Great, thank you for the intro. So I will be briefly summarizing the key results from the third paper in the LIFE series, in which we use atmospheric retrievals to derive first resolution and signal-to-noise requirements for the LIFE mission. And we do this by analyzing an Earth twin exoplanet. So we analyze simulated mid-infrared spectra of Earth. And the main question we aim to answer or start answering in this paper is, how good does life need to be? And so the aim for life is that we can use life to characterize terrestrial exoplanets in the habitable zone around their host star from their mid-infrared thermal emission spectrum. So basically the goal is that we could look at Earth 2.0 using life. The idea that we follow in this paper 3 of the series is that we simulate observations of such planets using LifeSim, and then we look at these simulations and study how well we could characterize this Earth-like planet from live observations. And the method we use is, so we generate a lot of different quality spectra. I'll explain briefly in a moment what this means. And then we run atmospheric retrievals on these different quality spectra and see how well we can characterize Earth given a certain spectrum. Now, the first thing I'd like to briefly address is what impacts the quality of a spectrum. And there are basically 3 main knobs we can turn. The first thing we can change is the wavelength coverage of the spectrum. And of course, the broader the wavelength range we measure the spectrum on, the more information we get about the planet and the stronger our constraints should be. So in the paper itself, we test different wavelength ranges. Here, I will not go into detail about this due to a lack of time. The next knob we can turn is the resolution of the spectrum. So basically how many data points we get per wavelength. And of course, the higher the resolution of a spectrum is, the more information on the planet is in the spectrum. And the last knob we can turn is the signal-to-noise ratio. So basically how large the error bars on the individual data points are. And of course, the smaller the error bars are, the stronger the constraints on the planet. I should mention that the wavelength coverage and the resolution of the spectrum are basically by default set by the design of life that we focus on. So once the instrument is built, the resolution and the wavelength coverage is sort of fixed. The signal-to-noise ratio is somewhat more flexible because, of course, we can achieve a higher signal-to-noise ratio by looking at an object for longer. But again, there are sort of limits to this, and one limit is how large the collector mirrors will be. So what we do then is we generate these observations with life. This might look something like this. So you have the spectrum that we would observe with life, and then we run an atmospheric retrieval on this. And the goal of the atmospheric retrieval is, in a nutshell, to go from the spectrum that we can measure to a characterization of the planet. And that involves finding constraints on the surface temperature of the planet, the radius, the pressure temperature profile of the atmosphere, and then also constraints on what gases are present in this atmosphere. Okay, now let's look at some at the results we get from these Earth twin retrievals. First of all, just briefly, what spectra do we use? We use simulated spectra of Earth. These spectra look somewhat like this. These simulated spectra are from a one-dimensional atmosphere model, and we model the molecular absorption features of various different atmospheric species, such as, for example, water and CO2 and ozone, and also methane. And for this first study, we assumed a cloud-free atmosphere. And then we simulated observations of this exoplanet around a sun-like star. So this planet we put in an 1 AU orbit around a sun-like star, so really an Earth analog, and put it 10 parsecs away from the observer and simulated spectra of variable resolutions, so resolutions 50 and 35, and then also variable signal-to-noise levels, so from 10 to 20. In the paper itself, we look at a way broader range of spectra, but here I will focus on this smaller range because this is where the interesting stuff happens. So let's look at some retrieval results. First, we can look at constraints on planetary parameters. So what we are looking at here is the radius of the planet, the surface pressure, and the surface temperature. And what you see up here is basically the retrieval results. And you see that the planet radius is extremely well constrained by our retrievals. Just for reference, this black point is the prior. So basically what we assume that is known about the planet radius before the observation with life. And you see that we can constrain the radius further with observations with life. And then also the surface pressure and the surface temperature are well constrained with life. Here, I don't show a prior because the prior range is basically huge. For example, for the surface temperature, the prior range is from 0 Kelvin all the way to 1000 Kelvin. And these results are also largely independent of the resolution and the signal-to-noise ratio of the input spectrum. So each point stands for a different resolution signal-to-noise ratio case. What you see, of course, is that if we go up in resolution and signal-to-noise ratio, the error bars get smaller, but the estimate is still sort of okay, even for the lowest resolution cases considered and signal-to-noise ratios considered. Then let's briefly look at some of the constraints for the atmospheric gases. So in the retrieval itself, we do not find nitrogen or oxygen in Earth's atmosphere. And this is mainly due to the fact that nitrogen and oxygen do not have significant absorption features in Earth's mid-infrared spectrum. However, what we can say from our retrieval results is that the bulk of the atmosphere, so the largest part of the atmosphere, does not have, is basically transparent in the mid-infrared. So we can tell from the surface pressure that we retrieve and from the other abundances that there has to be an additional gas in the atmosphere which is responsible for the bulk weight of the atmosphere, but doesn't have significant features in the mid-infrared. So there are some constraints on the bulk atmosphere. Then for the atmospheric trace gases, the results are shown here on the right. So basically we consider CO2, ozone, methane, carbon monoxide, water, and N2O. And we see that CO2, ozone, and water are retrieve or we detect all of these gases independent of the quality of the spectrum. So for low resolution and signal-to-noise cases and high resolution and signal-to-noise cases. In contrast, carbon monoxide and N2O are hard to detect, and this is mainly again because their features in the mid-infrared spectrum for Earth-like abundances are very weak compared to the noise, the expected life noise. So for an Earth-like atmosphere, we do not expect these trace gases to be detectable. Now, the interesting stuff happens for methane, where at low resolution and signal-to-noise ratios, we do not detect it. And as we go to the higher resolution and signal-to-noise cases, we start detecting methane. And methane is of interest to us because this is often considered to be a potential biosignature, especially if large amounts of methane are present simultaneously with oxygen and ozone. And again, these results for most gases are independent of the resolution and signal-to-noise ratio of the spectra. However, as I said, for methane, we do see a change, and we would state that a detection of methane is only possible for an Earth-like exoplanet if we have a resolution of at least 50 and a signal-to-noise ratio of at least 10. So to end off, just briefly, the take-home messages. So we run atmospheric retrievals on a grid of different simulated observations of an Earth twin with life. And we find that the radius, surface pressure, and surface temperature are all strongly constrainable with life. Then we manage to detect CO2, water, and ozone independent of the quality of the input spectrum with life. And if we want to detect methane in Earth's atmosphere, we would require a resolution of at least 50 and a signal-to-noise ratio of at least 10. Yes. So that is all that I wanted to talk to you about today. If you are interested in more details of these studies, please consult the manuscript. Unfortunately, I didn't have time to go into all of the details. Yes. Thank you.